motor bank calculations. In this presentation, what we're going to be looking at is how to size the conductors and overcurrent in a larger motor bank installation from section 28. First off, we should have a general idea what the term bank even means, and it means a group of that particular device fed from a common supply. So a motor bank would then be a group of motors from a common circuit. Now, there's a few different ways that this can be constructed, and one of them is this. Now, what you'll notice is that these three motors are connected to a single branch circuit, and that each of the motors will turn on at exactly the same time because there is only one motor controller. There are three different rules that we have listed here for the overcurrent that supplies all three of these motors, to the conductor that supplies all three of these motors, and to the tap conductors that would individually supply each of the motors from a common splitter. Now, 28206 covers the requirements for this because it's somewhat rare. 28206 says, yes, you can do it, but there are some specific requirements that you must ensure are in place prior to doing any of these three rules. And the first item that you see, and what is most commonly applied in the industry, is a maximum overcurrent of 15 amps. So that means that this single branch circuit with multiple motors is usually relegated to very small motor loads, as well as small applications where we would need all three motors to come on at exactly the same time, which is not very often. The more common application that we see for motor bank installations is something that looks like this. This is a multiple branch circuit arrangement where each of the motors is connected to its own individual overcurrent device, which means overcurrent to load. This is a branch circuit, 4 branch circuits, and then 1 feeder. The definition of a feeder being that a overcurrent that supplies energy to another overcurrent, the conductor, and therefore the circuit, is referred to as a feeder. This installation has 3 different rules that we are going to look at in order to establish the size of each of those conductors as well as the main overcurrent. You'll notice I put a blue line around all of the rest of the conductor mush down there, and that's because the rules for sizing that equipment don't change. These are dealt with as individual motors would be, and the applicable rules would apply. The only thing that we would have to size different is up here, the tap conductors, and we'll take a look at how that is done. So let's look at an example and start through the process. The first thing we're going to look at in this particular arrangement is the feeder overcurrent, which is located up here. I have 3 different motors, motor 1, 2, 3. All of them are skim, 3-phase. They each have different overcurrent devices. This is a time delay fuse, and that's a non-time delay fuse. These 2 motors are continuous duty. This one's non-continuous duty. And finally, a different type of starting method, which is an auto transformer, whereas motor 1 and 2 have a full voltage start. So let's first start with the feeder overcurrent device. The feeder overcurrent device is going to be covered under 28204 subrule 1, and it's a bit of a quirky process. Essentially, what we're going to do is this. We're going to take the largest calculated overcurrent and add to that the FLAs of the other remaining motors to get our maximum OC. However, what's odd about this is that we need to calculate the largest OC as though all motors have the same OC type as the feeder. Now remember, depending on what type of overcurrent we have, we might get different multipliers from table 29. The feeder in this situation is an overcurrent that is a breaker. And so what that means is that we are going to have to calculate what is the maximum OC for this one if it was a breaker. Well, that one is already a breaker, so it seems to make more sense. But we're going to do the same thing for this motor and for this motor. We have to figure out which one is the largest based on it being a circuit breaker overcurrent device. So the process then from 28204 is to establish which one is the largest. Well, motor 1, 20 amps times 2.5, and the multiplier I'm getting is from table 29, gives me 50 amps. All right, motor 2, 30 amps times 2, and it's times 2 because it's an auto transformer start from table 29, gives me 60 amps. Motor 3 is 40 amps times 2.5, and that gives me a 100 amp calculated value. Now remember, these multipliers that I'm doing right now have nothing to do with what is actually installed in the branch circuit. This calculation is purely to size this overcurrent here, the motor feeder overcurrent. So now we've established that obviously the 100 amp calculated value is the largest. And so what we're going to do is then take that 100 amp and add to it the FLAs of the other two remaining motors, which is 20 and 30. That gives me 150 amps. At this point, I'm simply going to take my value to table 13, and this is the absolute maximum that I can possibly put in this particular circuit. Table 13 renders exactly a 150 amp overcurrent device. This would be the largest that I would be permitted to place onto this particular arrangement of motors in a bank. So that's how I would establish the motor feeder for this particular motor bank. What about the feeder conductor? Well, the feeder conductor is located right here. And the feeder conductor under 28108 actually has a few different options based on what type of motors are placed into the circuit. If we look at subrule 1 item A, it's if all the motors are continuous duty. It gives us a process to go through in order to calculate the size of this conductor. But what if the motors are all non-continuous duty? Well, that would be subrule B. What if it's a mix of continuous and non-continuous duty? Well, subrule C would be used. And finally, subrule 2, what if the motors don't run at the same time? Let's say they're controlled in some way so that only this one can run, or those two can run, but they never all run at the same time. Well, then subrule 2 would be followed, and it's a pretty logical process. Now, in this situation, we're going to say that all the motors can run simultaneously, and that's the easiest and most common situation that we're going to see. And often, motor banks will be installed where we have pumps, multiple pumps, and they're all running off one main large breaker in a central distribution panel. And because of that, we need to then ensure that all of them can run at the same time for various different flows. So since we are doing all the motors running at the same time, and since my motors are not all the same duty rating, I have to go to item C. And item C, there we go. Item C is a mixture of both continuous and non-continuous duty motors. If we read through this rule, what it tells us to do is first establish the largest continuous duty motor and apply 125% to it. Then add to it the FLA of the remaining continuous duty motors. And in this situation, there is only one other continuous duty motor. It then says to add to this value the other remaining non-continuous duty motors at their multiplied values. So our 40 amps times 1.5 is motor 3, and that's a short time duty 30-minute rating. I add them all together, and I get 117.5 amps. That is the minimum value required, which means when I go to table 2, because I'm using copper, RW90, and conduit, I get a number 1 og, good for 130 amps. Now that's the main feeder conductor and the main overcurrent for this motor bank. But what about the tap conductors? The tap conductors are these conductors right here. And those tap conductors are actually going to be sized based on 28110, subrule 2. The tap length is very important, and the tap length is going to be used in order to determine how large do these have to be. If they're 3 meters or less, according to the rule, the tap can be the same size as the motor's branch circuit conductor, as in there would really be no difference in size from the tap conductor to the remaining conductors supplying the motor down below or downstream. If, however, we have a larger distance, 3.1 to 7.5 meters, larger of the two values indicated there is what we're going to choose. So 1/3 of the feeder conductor must be determined, and the motor branch conductor ampacity would be determined. Whichever one is larger would then be used to size the tap for that particular motor. So let's take a look at an example with these three motors and see if we can't calculate the tap values. So here are my three tap conductors, tap 1, tap 2, tap 3, because if you had not already figured it out, this is a splitter up above, and a splitter is simply something that we can connect various conductors of different sizes together without overcurrent protection when the conductor size drops. So we've got a large conductor coming in here, and then smaller conductors coming out the splitter. We're using copper RW90 conduit, and I put in here EMT because the rule says if we're doing taps that are less than 3 meters in length, they must be housed in EMT or metal conduit. So let's look at the first motor. I'm going to say the first motor has a tap length of 3 meters. So what that means is that all we have to do is go through the standard sizing for a motor branch circuit without any sort of special application, since it is a tap conductor. So 20 amps times 1.25, due to the fact that the motor is continuous duty, full voltage start, circuit breaker. The only thing that really matters is this, continuous duty, right? And we get 25 amps. We go to table 2 in the 75-degree column, and we get a number 12, good for 25 amps. Motor 2, I'm going to say, is also quite short in length. The tap conductor is very short. It's 2 meters, and that again means that the 30 amps times 1.25, being that it is continuous duty, is all we need to do in order to validate the size of the tap conductor. Now again, the conductors that we're calculating are here and here. The next motor is longer tap length. It's 6 meters. So the first thing I'm going to do is calculate what the branch circuit conductor size would be. So 40 amps times 1.5, I'm simply going to get the minimum ampacity, which is 60 amps. This is the first value that I need to know because this exceeds 3 meters. It means I also need to know what is 1/3 of the ampacity of the feeder conductor. The feeder was a number 1 odd, good for 130 amps. And when I divide that by 3, I get 43.3 amps. At this point, what I would be doing is evaluating which of these two is larger. Now, in this situation, it's quite obvious. Motor 3, the actual branch circuit conductor size, is going to render a much larger conductor. And because of that, 60 amps will be used in order to size the tap conductor. 60 amps from table 2 gives me a number 6 og, good for 65 amps. Now this brings us to the end of our presentation on motor bank sizing and motor bank conductor and overcurrent applications.